All right, so it's been a few minutes, so we'll go ahead and get started with class today. Uh, See a few people are following me. Can you guys see my screen all right? Yes, no. Okay, well, no one's saying they can. So, okay, today's topic is something called um modular arithmetic. And so don't be scared by the vocabulary. Modular arithmetic just means we're looking at remainders. Right? So when we think of remainders, we think of, well, okay, let's take like 107. And we want to say, hey, what is the remainder when 107 is divided by 5? So we can divide, right? 107 divided by 5, go into 2, 7, 1, subtract 5, and it's 2. So our remainder is 2, right? And so this is sort of the basis for modular arithmetic. Essentially, we make notation or symbols in order to express this without having to say like 107 divided by 5 has a remainder of 2. Instead, we can do something like this. So it'd be 107 equals. Note this is 3 bars, 2, and then mod 5. So let's break this down a little bit, right? So 5 is what we're dividing by, and it's going to be next to this mod symbol. And mod, once again, just stands for modular. And then 2 is our remainder. So this is our divisor. And this is our quotient, the number that we're dividing. And so if we rewrite it, right, it'd be 107 divided by 5 leaves a remainder of 2. So let's do some practice. Let's say we have the number 215. Um, and I just want you guys to find the value of this question mark. So I'll give you guys just a couple of minutes to think about that. And then I'll go over it. And if you have an answer, feel free to DM me or Arush. And we can tell you if you're right or not. Okay, so it's been a few minutes. So let's just go over this real quickly. So remember, right? This is the number that we're dividing by. This is our remainder. and this is what we're dividing by. So really, all we're doing is we're finding the remainder, right? When 215 is divided by 7. So we do this, right? And then that goes into that 0 times. So the remainder is 5. So for this syntax or writing it this way, we would put a 5 here. So 215 is 5 mod 7. And remember, all this means is that it leaves a remainder of 5 when you divide by 7. And then real quick, we'll just do one last practice. Let's do 811 mod 11. So same deal. We're just going to do a little bit of practice. If you guys have any answers for this, you can DM us, just like the one before. Okay, so just like the other one, right? We're just trying to find the remainder when this number is divided by this number. So 811 divided by 11, we put in 7, so minus 77, and then 41, and then we can put in a 3, and so our remainder is 8. Okay, so now that we've sort of got the basics out of the way, now we want to talk about some properties, right? And why this is useful. Um, and so really the main point of this is that we can add them together. So what I mean by that is we have A1 is B1 mod n, and A2 is B2 mod n. What we can say is that A1 plus A2 is going to be equal to B1 plus B2 mod n. Right? So if we have A1, it leaves a remainder of B1 when we divide by n. A2, it leaves a remainder of B2 when we divide by n. When we add these two numbers together, they're going to have a remainder of B1 plus B2 when we divide by n. So an example of this would be something like 71, right? 71 is 7 mod 8. And also, let's say 9, right? 9 is 1 mod 8. 71, right? Because if we subtract 64, then we have 7, which is the remainder it leaves when divided by 8. And then for 9, right? 9, obviously, we put 1 8 into it, and our remainder is 1. So that's the reasoning here. And so what we can do with these two things is we can add them together. And what happens is we have 80 equals 8 mod 8. So this number should never change, right? Because it's sort of what you're dividing by. But these numbers you can add together. So just keep that in mind when you're doing when you're adding modular equations together, right? And so 8 mod 8, right? That's the same as saying 0 mod 8, right? Because it leaves a remainder of 0 when you divide by 8, right? Leaving a remainder of 8 when you divide by 8 is just 0, because when you divide by 8, you can just put that multiple as part of the quotient. And so, yeah, this is true, as we can see, because it gives us a true statement, right? 80, when you divide by 8, leaves a remainder of 0, which is true. And so this is one of the properties that we can use. Another property we can use is the fact that if we have A1 times A2, this is equal to B1 times B2 mod n. And so just like the other one, really what we're doing is just we're combining these two together, but this time instead of adding, we're multiplying. Um, and so we can use the same example, right? 71 equals 7 mod 8, and 9 equals 1 mod 8. And so we can multiply the two numbers together, and we should get 639, right? And this will be equal to 7 times 1 mod 8. So this is going to be 639 is 7 mod 8. And this is true, right? Because 640 is a multiple of 8. So that means if we subtract 1, it's going to leave a remainder of 7 when we divide it by 8, right? Okay, and so another way this would be used is say I said like 7 to the power of 30 is equal to 1 mod 8. So it leaves a remainder of 1 when you divide by 8. Then the question would be, what is the remainder that's left when we divide 7 to the 32 by 8? And so there are actually a lot of different ways you could go about doing this, right? Um, and so the first way would be, okay, we have 7 to the 30 right now. We want to get to 7 to the 32. So an idea could be we take 7 to the 30, 1 mod 8, right? And we can multiply by 7. Um, and so what this would mean is like for this equation, right, we can multiply by 7 to this side. And what we would get is 7 to the 31 is 7 mod 8. And then we can multiply by 7 again. And so this would get us 7 to the 32 equals 49 mod 8. And so we can simplify this further as well, right? Because 49 mod 8, if we get rid of all the multiples of 8, right? So 49 minus 48 is the largest multiple of 8, is going to be 1. So this is the same thing as 1 mod 8. So that's one way of doing it, is that for modular equations, you can multiply both sides by the same thing, and your equation will still hold true. And so similarly, if you wanted to find like 7 to the 30 plus 1, well, you would just add 1 to both sides. So this would be 2 mod 8, right? And so if we were doing like, say, 7 to the 30 plus 12, right? This would be, well, we add 1 to 12, so we'd get 13 mod 8. And then, of course, we'd have to simplify, right? Because we don't want 13 because it's greater than 8. We want the remainder. And 13 is not really a possible remainder. So we'd subtract 8 and we get 5 mod 8. And so this is one way. And another way to do this is to actually consider something where we look at negative remainders. And so what I mean by that is like, so we know 7 is 7 mod 8, right? If you divide 7 by 8, you you put 8 into 7 0 times, and your remainder will be 7. But what we can also do is if we have something like mod 8, what we can do is we can actually change one side and not change the other side, and the equation will still hold true. And that's only if we add a multiple of this number. So what that means is we can say 7, and then we can add an 8, right? 7 is equal to 15 mod 8. And this makes sense, right? Because 15 is essentially the same as 7. It just has one more 8. So the remainder is going to be the same. And likewise, we can actually subtract 8. So when we subtract 8, right? 7 minus 8, well, that's going to be negative 1 mod 8, right? And so for a problem like this, um, what we can sort of imagine doing is, right, 7 to the 32 or 7 to the 30. Technically, you don't even need the 7 to the 30, so we should just ignore it for now. But 7 to the 32, right? We want to figure out what this is, mod 8, right? So we can think back to what we learned, right? If we have two equations, say 7 equals negative 1 mod 8, and 7 equals negative 1 mod 8, recall that we can combine these, right? We can combine them by multiplying them together. So what we will get is 7 squared is the same as negative 1 times negative 1 is 1 mod 8. And so what we can end up doing is we can keep multiplying by the same equation over and over again, right? So 7 to the third is going to be equal to negative 1 mod 8. And so if you keep doing this, right, you're just multiplying by negative 1 each time here. So if 7 is negative 1 mod 8, right, and then 7 squared is 1 mod 8, it really just flips between negative 1 and 1. So 7 to the 32, right? 7 to the 32, 32 is an even number. So on an even number, right, we're going to have an even number of negative ones multiplied with each other. So that means that this result is going to be 1 mod 8. Does this make sense so far, guys? Do you guys want some more practice with putting modular equations together, like multiplying them and adding them? Or sure, yes. Okay. So I guess we can do like say 56, right? 56 is going to be equal to 1 mod 5. And then I don't know, 78 is equal to question mark. It's equal to question mark mod 5. That's not a good problem. Oh, we could do something like this, maybe then, right? And so maybe a question would be like, um, what is x plus 1 mod 5? So I'll give you guys a second to think about this. Yeah. So just be aware, right, that now we have a variable in play, and we're not just adding numbers together. So keep in mind what you want and what's given, and try your best to put them together and see if you can solve this. And if you have any answers, just DM me or Arush once again. All right, so it's been a couple of minutes. So let's look at this problem, right? So really, what we want to realize is we actually don't even need this, right? This is kind of just like a distractor. And sometimes what you'll see on problems is a distractor like this. So it's important to focus on what you want, right? And not try to overcomplicate things. So yeah, we don't need this, but an idea is, right, you can add them together, and it would get you the same answer. But really what we're looking here is we just want, right, this. And so if we add one to both sides of the equation, it's just going to give us this, right? And so we're done. All right, here's another idea. Say we have like A equals yes, x plus 1 is equal to 4 mod 5 is the answer. So let's say A is equal to 14 mod 15. Why is it 3 bars? It's 3 bars because we don't want it to be 2 bars because 2 bars means, yeah, 2 bars means they have to be exactly the same, right? So 3 equals 3, um, x equals x. But 3 bars, right? We're sort of bending the rules a little bit because 3 bars, we could say 14 is the same as 0 mod 7, but we could also say 21 is the same as 0 mod 7. And clearly, right, 14 does not equal 21. So this is sort of the idea is that we want a different set of equal signs than what we would normally use. All right. Just like cut this off here so you guys know what I'm trying to get at. So let's say we have A equals 14 mod 15, and B is 13 mod 15. C is 12 mod 15, and D is 11 mod 15. Find A, B, C, D mod 15. So I'll give you guys some time to think about this problem now. And yeah, if you have any answers, just DM them to me, um, or any questions too. Okay, it's been a couple minutes, so let's see how to go over this, right? So the first instinct, right, is to multiply them all together, right? Because we said earlier that we can multiply equations together. So really, A, B, C, D is just going to be 14 times 13 times 12 times 11 mod 15, right? But this is a lot of calculation, right? Um, I think this is going to be like 182, and then this is going to be 132, right? And so the numbers get very big very fast. And especially on the AMC 8, where you want to conserve time, if you see something that's like really big or takes a lot of time, you might want to reconsider how you do the problem, right? But I mean, if this is like a later problem and you know you can get it right as long as you do the calculation, then by all means you should spend the rest of your time just solving the problem if you can get the right answer. But if you're sort of low on time and you need to get to other problems, it might be better to try to think of a better way to do this, right? And so the idea here is we can make the calculations a lot simpler if we just consider each number in a different way, right? So my idea is A equals -1 mod 15, right? And remember, I can do this because everything is in terms of dividing by 15. So adding 15 to either side won't change anything, right? A is -1 mod 15 is the same as 14 mod 15. And similarly, I can do B equals -2 mod 15, right? Because 13 is 2 less than 15. And so we can do this all the way down. And now our problem has gotten a whole lot simpler, right? Because all we have to do is multiply these four numbers together, right? So A, B, C, D is -1 times -2 times -3 times -4 mod 15. And so this is just going to be 24 mod 15. And so we should simplify this, right? Because 24 is bigger than 15. So we subtract 15, and this gets us 9 mod 15. So if you were sort of stuck on this very large calculation, um, think about the tools you can use to make problems like this simpler and easier to calculate so that on competition day, you're ready and you're solving problems as fast as you can. So yeah, the answer is 9 mod 15. Okay, I think we had some pretty good practice with this. So I'm going to bring up one formula. But before that formula, I'm just going to bring up like sort of a little fun fact, but sometimes it's useful. So it's just something to keep in mind is if we have a number squared, it is always going to be 1 or 0 mod 4. And so the reason for this is um, if we have an even number, so an even number would be of the form 2n, right? It's going to be a multiple of 2, and any number of this form is an even number, right? An even number squared is going to be 4n squared, right? And so we know that this is going to be a multiple of 4 because there's a 4 in front. So that's where a perfect square could be 0 mod 4, right? Leaves no remainder. On the other hand, if we have an odd number, right, an odd number will have the form 2n plus 1. So you take an even number and then you force a 1 onto it so that it becomes odd, right? So like 2 times 2 is even. We know that for sure. And then to make it odd, we just add 1. We're like 2 times 70, right? Add 1, make it odd. So 2n plus 1 squared, right? If we FOIL this out, is going to be 4n squared plus 4n plus 1. And so we can say, right, that this part right here, that's a multiple of 4, right? Because we have this 4 in front. So this part is going to be 0 mod 4, right? Leaves no remainder when we divide by 4. And then if we add a 1 at the end, well, this is 1 mod 4. So if we add these two together, we're going to get a total remainder of 1. So if you have a perfect square that is odd, then it's going to be 1 mod 4. And if you have a perfect square that is even, it's going to be 0 mod 4. This is just good to know. It can be really useful for problems like, actually, yeah, let's do this problem. So we have positive integers a and b, and a squared plus b squared is equal to 703. And it says find the number of uh, ordered pairs, or essentially combinations of a and b that satisfy this. So I'll give you guys a few minutes to think about this. But yeah, I would encourage you to try to use the fact that we learned up here for this problem. Okay, so it's been a couple of minutes, and so this is a little bit of a harder problem. But if you really understand modulos and sort of logic your way through it, it's actually not too difficult. So for this problem, right, your first instinct might just be to try a bunch of numbers, right? Oh, what if B is like 26, right? And then you say, okay, well, B squared is 676. And then, oh, you subtract, and then you say, oh, there's no solution for A. It doesn't work. And then you might go down to the next one, 25, and then A doesn't work again. And you might do this for a while and realize, hey, this is going to take a long time. And so when a solution starts to take a long time, right, you have the choice of continuing, but in most cases, you want to find the best way. And so the best way here is to use this fact, right? Perfect squares have to be 0 or 1 mod 4, right? So let's take a look at what that means for this problem. So a squared plus b squared equals 703. Right? And we can actually simplify this to a squared plus b squared is 3 mod 4, right? Because 703, when you divide by 4, leaves a remainder of 3. And so now we can sort of think, right? Well, if a squared can be 0 or 1 mod 4, and b squared can also be 0 or 1 mod 4. But the problem here now is there's no way that we can use zeros and ones to get 3, right? 0 plus 0 is going to give us 0. 0 plus 1 is going to give us 1. And 1 plus 1 is going to give us 2. It's not possible to make 3 from 2, either 0 or 1, right? And so, in fact, the answer to this problem is actually nothing. There are no pairs A and B that can satisfy this. Does that make sense? Okay. Well, I don't see any questions, so now I'm going to go over that formula I was talking about. So, um, I believe this is called Fermat's Little theorem. And it's just really helpful for finding remainders for very big powers and exponents. So what I mean by that is this formula says for a prime p, and p doesn't divide a, it's true for all numbers a that a to the p minus 1 is equal to 1 mod p. Right, and so let's do an example of this, right? So let's say we want 5 to the 2025, and we want to find the remainder when it's divided by 7, right? Well, we want to use Fermat's little theorem. What Fermat's little theorem says is this, right? And so we can translate this. So our A is going to be 5, right? Our P is 7. So what we can say is 5 to the 6th is equivalent to 1 mod 7, right? It leaves a remainder of 1 when we divide by 7. How does this help us here? Well, like in a previous problem, we can keep stacking these equations together, right? So 5 to the 6th, if we multiply these equations together again, right, this is still going to be 1. So 5 to the 12th is still going to be 1 mod 7. And so as long as this power is a multiple of 6, it's going to be 1 mod 7. So if we sort of look at 2025, we can sort of hit into the ballpark of 2025. And the closest multiple of 6 is 2022, right? So we know that since 2022 is a multiple of 6 here, right? We can multiply all of those equations together. So imagine there's like 2020, not 2022. What is it divided by 6? 18, 22, 337. Imagine we have 337 of these, and we're just multiplying them all together, right? In the end, we're going to have 5 to the 2022 on this side, right? Because we have 337 times 6. And over here, it's just a bunch of ones multiplied together. So this is still going to be 1 mod 7. And so now that we're in the ballpark, right, we can simply multiply by a 5 to the third, right, to both sides. So now, right, over here we have 5 to the 2025, which is what we want, and that's equal to 125 mod 7. So now all we have to do is simplify this. How many times does 7 go into 125? Well, 1, and then an 8, nope, not an 8, a 7, right? Then we 49, and it's 6. So in the end, this is simplifies to 6 mod 7. And so we know that 5 to the 2025 has a remainder of 6 when we divide by 7. So that's how we use this formula. Um, yeah, this one is a pretty important one. I mean, sometimes it's a little bit more niche. You might not see it as often, but if you get a problem like this, it turns a very hard problem into a pretty simple problem, I would say. All right, so that's about all I had for class today. So let's say meet back at 7 for the problem solving session. And until then, you guys are free to go on break. So see you then. And if you have any questions, feel free to ask me or Arush, and we can answer. Okay, so it's 7 now, so you guys should be coming back from your break, and I posted today's worksheet in the chat below, and I'll also post it to our Google Classroom. As usual, if you guys have any questions, feel free to DM me or Arush, and we'll tell you if you're on the right track, and give you guys hints to help you guys solve some problems. Okay, so our problem solving session was a little bit shorter today. Um, so yeah, we're gonna start solutions right now. So if you guys have any problems you want to see solutions to, just post them in the chat, and me and Arush can go over them. Any suggestions? If not, then I can just start from number one, and we'll work our way up to number nine. So the first problem says, find the smallest integer that leaves a remainder of 5 when divided by 11 and a remainder of 2 when divided by 8. So 5 mod 11 and 2 mod 8. And I just say for the purposes of the AMC 8, really what you can do is just start listing out the possible combinations. And it shouldn't take too long before you find the right one. Oops, that's not 21, right? So we'd go up by 11 every time. And then it'd be 2, 10, 18, 26, 49, 60, 71, 82. Oh, would you look at that? We found our answer, right? It should be 82 because um, 82 will also show up here because 8 times 10 plus 2 is 2 mod 8. So yeah, there's our answer. Any questions? Okay, let's move on to number two. Find the remainder when 2 times 4 times 7 times, okay, 2 times 4 times 7 times 8 times 11 is divided by 15. So this mod 15. Okay, so, right, we're going to use the process that we learned in class. Except for here, right, what we can do is we can actually pair numbers together, right? So 2 times 7 um, is going to be 14, and then we're going to have 4, 8, and 11. And so now what you can do is, hey, 14 can be written as -1, remember, right? If we subtract 15. And also here we have 32. And 32 is actually 2 mod 15, right? Because 30 is a multiple of 15. So we're going to have 2. And then 11 we can write as -4. So our total is going to be 8. So that's our answer. Number three, find the smallest positive integer greater than 1 that leaves a remainder of 1 when divided by 4, 5, and 6. All right, so 4, 5, 6, they're all 1. Mod these numbers, right? And so the idea here, right, is we can sort of create this number by multiplying what we have here. So we make a number that's divisible by 4, 5, and 6, and then we simply just add 1, right? Because that number will now be 1 mod each of those numbers. So what's divisible by 4, 5, and 6? Well, we would have to take the least common multiple, and that would be 4 times 5 times 3, which gives us 60. And so 60, we want 1 mod, so our answer is 61. Okay, starting with some gold coins and some empty treasure chests, I tried to put 9 gold coins in each treasure chest, but that left two treasure chests empty. So instead, I put six gold coins in each treasure chest. But then I had three gold coins left over. What was the least number of gold coins I could have? Okay, so essentially, we have a certain number of treasure chests, right? And if we put nine in each, so it'd be like nine and nine, then we have two chests left over. So actually, let's call the number of chests C. Um, so we know that 9 times C minus 2 is the number of coins that we have. Um, and then, so I put six gold coins in each treasure chest, but then I had three gold coins left over. So what that means is we put six coins in each treasure chest, and you have three left over. So now we have the number of gold coins in an expression, in two different expressions, so we can solve for the number of coins. So we have 9c minus 18 equals 6c plus 3. So 3c equals 21. So c is going to be 7. So in total, we have 7 chests. And so that means the number of coins is 6 times 7 plus 3. Oh, I don't know why that's there, which gives us 45. Okay, and I think Arush will take it away for the last five problems.
Okay, so problem five, let me just check real quick. Uh the number n is a two-digit number. When n is divided by 9, the remainder is 1, and when n is divided by 10, the remainder is 3. So the second one, since we can actually determine from the second fact that n's one digit must be 3, and then we can just list them all and then find which one has a remainder of 1 when divided by 9. So let's just list them all real quick. Also, sorry for bad handwriting. So these are the numbers. We just need to subtract 1 from each of them, and whichever one is divisible by 9 is our number we are looking for. So 2, 12, 22, 32, 42, 52, 62, 72. So 72 is divisible by 9. So 73 leaves a remainder of 1 when divided by 9. So we just need to find the remainder when this is divided by 11, I think. And we know that 11 times 6 is 66. So 73 minus 66 is 7. So I think 7 is our answer.
Yep.
All right, sixth problem. Let me just check what that is. What is the remainder when 7 to the 2024 plus 7 to the 2025 plus 7 to the 2026 is divided by 19? So this, I think, was on the AMC 10 last year. So I think I remember how to do this one. So, wait, let me just write it out. So what I would do is I distribute out a 7 to the 2024 since they each share that. So you'd get this. And then we also can evaluate this portion. So 1 plus 7 plus 7 squared is 57. And we also can figure out quickly that 57 is divisible by 19 since 19 times 3 is 57. And since that is divisible by 19, then so is the entire expression. So this is divisible by 19 and it leaves a remainder of 0 when divided by 19. So that was that problem. Let me just check what the next problem was. Uh, Problem 7, what is the units digit of 2022 to the 2023 plus 2023 to the 2022? So for a, let me just write out the expression first, actually. So we have this. So personally, what I would do here, instead of like just doing modular arithmetic, there's this easier solution. So we just want to consider the last digit of both of the bases. And then if you like raise it to like 1, 2, 3, 4, and so on, like you'd get 2, 4, 8, 6. And then this cycle will actually keep repeating. So based on what modulo 2023 is mod 4, it would be one of these four. So if it's 3 mod 4, it would be 8, 4 mod 4, 6, 1 mod 4, 2, and 2 mod 2 is 4. So you can quickly tell that based off previous class, like when you divide the last two digits by 4, that's the same as dividing the entire thing by 4 and finding the remainder. So 23 is 3 mod 4. So the last digit of 2022 to the 2023 is 8. And then we can do the exact same thing. This time it would follow a cycle of 3971 since the base is 3. And then since 2022 is 2 mod 4, I think, then you'd get 9 for the resulting units digit. And then finally, 8 plus 9 is 17, which is 7 mod 10. So the units digit is 7. Let me just check the next problem. So problem 8, for perfect squares A and B, find the number of possible remainders when A plus B is divided by 4. So if you remember earlier, we talked about a fact saying that if A is a positive integer, then A squared must have a remainder of 1 or 0 when divided by 4. So there are three cases we have to handle here. If A, so if A squared, if one of them is 1 mod 4, and then the other is a 0, then if you add them up, you just get A squared plus B squared is 1 mod 4. The second case is if both of them are 0 mod 4, then if you add them up, you'd get, then you'd just basically get 0. So that can be a potential remainder. And then if you have 1 mod 4 instead, for both of them. You'd get a 1 plus 1, which is 2 mod 4. So that is three possible remainders. So 1, 2, and 0. So the answer is 3. And then last problem I check. Uh, find the second smallest positive integer x such that the expression x squared minus 1 is divisible by 100. So for this one, I don't know how you would actually do it using a modular arithmetic. So I just use like stuff we learned from previous classes. So we know that x squared minus 1 is equal to x plus 1 times x minus 1. So let me just write that. So we would have this. And then you should immediately notice that if x is equal to 1, then the product, x squared minus 1 is 0, which is divisible by 100. But then we have to do a bit of digging here and find out what other possible value of x has this divisible by 100. So, first of all, 100 can be rewritten as 5 squared multiplied by 2 squared. So, immediately you should notice that x plus 1 and x minus 1 must be both odd or both even. And if both of them are even, then they have a factor of 2. They both have a factor of 2. So the product would immediately have a factor of 4 in it. So we just want x to be odd so that x plus 1 and x minus 1 are both even. And then also to handle the 5 squared, if we make a like x plus 1 5, then that makes it odd, so that wouldn't work. So it also has to be an even multiple of 5. So 10 and so on and so forth. But here's the thing, both x plus 1 and x minus 1 can be multiples of 5 at the same time. So we have to have one of the two do all the work. So we can just have x plus 1 be an even multiple of 5 squared, which is 50 at least. So then x would be 49, which would give us 50 times 48, which is divisible by 100 because 50 times 48 is 2,400, I think. So yeah, so the second smallest positive integer x must be 49. And there you go. Also, sorry for the bad handwriting. I was on a computer because my original device was dead. So yeah, maybe better handwriting next time.
Okay then. So yeah, that's all we have for class today. So you guys are free to leave.